In this video, we are going to discuss something called the CMOS sizing, which is basically the designing of the size of the transistors, of the PMOS transistors and the NMOS transistors in the CMOS logic gates. So we need basically in this video at the end to be able to design W over L of all transistors in our logic gate, whether it's an inverter or any general logic gate. So the first question is, why do we need to design W over L? Why do we need to design the sizing of the transistors in any logic gate? Let's go back to the beginning of the story. We talked before about a capacitance that appears at the output between the output and the ground, which we call the stray capacitance, that appears due to the proximity between the components or the proximity between the wires in your small chip. This will cause a capacitance to appear, and this capacitance, when the output wants to change from low to high, okay, then the capacitor is going to charge through the PMOS transistor, okay, when the output wants to change from low to high, then the capacitor needs to charge, and when it charges, it will charge through the resistance of the PMOS transistor. Let's call it RP. So it will see a resistance of this transistor, which is RP, and the capacitor will charge through it. And then in the other case, when the output wants to change from being high voltage to low voltage, then the capacitor is going to discharge through the NMOS transistor, and hence it will see, the capacitor will see the resistance of the NMOS transistor, which let's call it Rn, for example. So the capacitor basically in the inverter is going to charge through the resistance Rb of the PMOS transistor, and it's going to discharge through the resistance Rn. The first piece of information that we need to know here is usually we need both transistors, the PMOS and the NMOS in the inverter, to have same driving capability of the current, same driving capability of charging and discharging the capacitor, which means that we need the speed of charging the capacitor to be the same as the speed of discharging the capacitor. In order to do that, we need to design the resistance of the PMOS through which the capacitor is charging to be equal to the resistance of the NMOS through which the capacitor is discharging, so that during the charging or during the discharging, the capacitor will take approximately the same time. So this is something that we prefer when we design the CMOS inverter, so that the time it will take, the output voltage will take in order to go up or to go down, it will be symmetric, it will be the same. So we need to design the resistance of the PMOS transistor to be similar to the resistance of the NMOS transistor. The resistance in general of any transistor, they found that the resistance is basically the voltage over the current, the voltage VDS over the current IDS. And because the current, it depends on the factor K. The factor K, whether Kn or Kp, multiplied by some voltages. So they said that R, the resistance of any transistor, is inversely proportional to the factor K. So Rn is inversely proportional to Kn, and Rp is inversely proportional to Kp. So if you want to design Rn to be the same as Rp, then you need to design Kn and Kp to be the same. So Kn, we know that Kn is mu n C oxide W over L of the NMOS transistor, and Kp is mu p C oxide W over L of the PMOS transistor. So here, if you want to design, assuming that C oxide is the same in both cases, if you want to design Rn to be similar to Rp, then you need mu n W over L of the NMOS transistor to be equal to mu p W over L of the PMOS transistor. All of this I'm talking about the CMOS inverter. So I didn't discuss yet the bigger logic gates. So for the CMOS inverter, you need the NMOS to have the same resistor as the PMOS, which means that Kn must be designed to be equal to Kp, and mu n W over L, the mobility of the electrons multiplied by W over L of the electrons of the NMOS equals the mobility of the holes multiplied by W over L of the PMOS transistor. But we know from physics that the mobility of the electrons is usually greater than the mobility of the holes. This will tell us that because the mobility of the electrons is greater than the mobility of the holes, you expect always that W over L of the PMOS must be greater than W over L of the NMOS. So because the mobility of the electrons is greater than the mobility of the holes, okay, then this will lead that in order for this equation to be satisfied, W over L for the PMOS must be greater than W over L. It's greater than, not necessarily very much greater than, so it's greater than is enough. So this will lead that the W over L of the PMOS must be designed to be greater than W over L of the NMOS. And this is something in our hand, is to design the PMOS transistor with W over L greater than W over L of the NMOS, so that this equation is satisfied, and hence we'll have similar or symmetric driving capability for the capacitor, charging and discharging of the capacitor. So usually we design W over L of the PMOS and W over L of the NMOS to satisfy this equation. And as a piece of information, as a side piece of information, usually L is chosen to be the minimum size that we can implement in practice. So for example, if you are using a technology that can implement 1 nanometer as the smallest size, then you take L as 1 nanometer. And then you design W to satisfy this equation. So L will be the same in both cases, which is the smallest size that you can implement or that your technology allows. So L usually is taken as the smallest size that your technology allows, and then they design W so that W over L n multiplied by mu n equals W over L p multiplied by mu p. So usually L is chosen to be the smallest size that the technology allows. And then W comes in the design, you choose W based on this equation. So this is the reason why we need to design W over L of both transistors, of the N and the P, in order to satisfy that the resistance of the P during charging the capacitor equals the resistance of the N during the discharge of the capacitor. And you expect always that the W over L of the PMOS will be always greater than W over L of the NMOS, and this is because the mobility of the electrons is greater than the mobility of the holes. So this is for the inverter. Let's now move to bigger logic gates. What happens if we deal with bigger logic gates? If we have a bigger logic gates, we have a problem. Why? Because in the pull-up network and the pull-down network, we don't have only one transistor. We have some combination of transistors connected together. For example, let me give you an example. Imagine that in a certain logic gate, we have n transistors connected in series, n PMOS transistors connected in series. This is in a certain logic gate, in some logic gate. And let's not talk about the pull-down network for now. Let's focus on the pull-up network. We are always interested for any logic gate to have the same speed as the CMOS inverter. So we want, when we design any logic gate based on CMOS technology, we want the logic gate to have the same speed as the CMOS inverter. And the speed comes from where? Comes from the speed of charging and discharging the capacitor, the speed that the V output goes up and V output goes down. So this is what determines the speed. This is what determines the maximum frequency that you can use, because you cannot use higher frequency than the speed of charging the capacitor. If you use higher frequency than the speed of the capacitor charging, then before the capacitor charging, you are going to go down. The volt input is going to change, right? And before the capacitor, the voltage of the capacitor goes down, the voltage input is going to change. So the frequency that you can use, the maximum frequency that you can use, depends on how fast this capacitor charges and discharges. So always when we design any logic gate, we are interested to have the same speed as the CMOS inverter, not slower. The same speed or more. Okay, so now if you have a gate like this, and you want to have the same speed, you have the same capacitance at the output, the same capacitance, and you want this gate and the CMOS inverter to have the same speed, then you have to design the total resistance of the pull-up network to be as RP, similar to the resistance of the pull-up network in the CMOS inverter. The resistance here of the pull-up network was the resistance of one transistor, which is RP. Here we have many transistors, so you have to design the total resistance of all the transistors here. Let's say they are N, transistor number 1, transistor number 2, transistor number N. You have to design all of them so that the total resistance is the same as the resistance of the CMOS inverter, which is RP. Which means what? Which means that you have, since they are connected in series, this means that you have to design the resistance of each of them to be RP over N. RP over N, RP over N, right? And so you have to divide the resistance over N. The resistance of each of the transistors here in this logic gate must be 1 over N of the resistance of the PMOS transistor in the CMOS inverter case. And since the resistance is divided by N, what happens to W over L? We mentioned before that the resistance is inversely proportional to K, which means that it is inversely proportional to W over L. So if the resistance is decreased by a factor N, then W over L is going to increase by a factor N. Which means that if W over L here, if W over L of this transistor, W over L of this PMOS transistor, let's call it P for simplicity. W over L of this transistor is going to, we are going to call it P. Then you have to design W over L of this transistor to be N multiplied by P. N multiplied by P. This is W over L of this transistor. And the same, W over L of this transistor, it has to be N multiplied by P. Why? Because the resistance is divided by N, so W over L must be multiplied by N. The resistance, RP, it was divided by N. And since the resistance is inversely proportional to W over L, then W over L must be, W over L of the CMOS inverter must be multiplied by N. So we multiply P by N. This is P, W over L here is P. Here W over L will be P multiplied by N. Let's write it clearly. So W over L of this transistor will be P, which is W over L of the PMOS inverter, multiplied by N. Same here, N, P. Same here, W over L will be P multiplied by N. So here, when you have transistors in series, you have to divide the resistance of the transistor there in the CMOS inverter by number of transistors. And since you are dividing the resistance by the number of transistors, W over L will be multiplied by the number of transistors. So you have to increase the size of W over L here over the one used in the CMOS inverter so that you have smaller resistance. That's why we need to design W over L of the transistor so that we have the same speed. So here we have a resistance RP because we had one transistor only. Here we have many transistors, so you have to design the resistance of each of them to be RP over N. So you divide the resistance over N, which means that you will multiply the W over L by N. Same for the pull-down network. If you have a pull-down network, let's say with some series transistors, NMOS, let's say 3 in this example. If you have pull-down network with 3 series transistors and you need the same speed of this logic gate as the CMOS inverter, so here the resistance of the NMOS transistor, the resistance of the pull-down network here, it was Rn. In order to have the same speed, the total resistance of the pull-down network here must be Rn, which means that you have to design this transistor to be Rn over 3, Rn over 3, Rn over 3. This is with respect to the resistance. What about W over L? Since you divided the resistance by 3, W over L must be multiplied by 3. So W over L of this transistor must be 3 times W over L that we use for the NMOS here. So let's assume that W over L here, W over L of the NMOS transistor of the CMOS inverter, well, let's call it N. So this is W over L of the NMOS transistor in the inverter. We will call it N for simplicity. So here, since you divided the resistance by 3, you are going to multiply W over N by 3. So 3N, this is W over L of this transistor. 3N, this is W over L of this transistor. 3N, this is W over L of this transistor. You see what's happening? So here, because we have 3 transistors in series, we have to divide the total resistance of the inverter there, which was Rn, by 3. So that the total resistance, when all the transistors work together, the total resistance will be the same as the CMOS inverter, Rn. But because you divided Rn over 3, you have to multiply W over L by 3, right? Because the resistance is inversely proportional to W over L. So you have to multiply W over L of the inverter by 3 in order to design this transistor. Its W over L must be 3N. So this is the case, very clear, for transistors in series. If you have transistors in series, you have to divide the resistance by the number of transistors, and hence you will multiply W over L by the number of transistors. Which W over L that you multiply? W over L of the CMOS inverter. You have here, it's called P. Here you are going to multiply by N. It will be NP. For the pull-down network, we called it N. Here it will be multiplied by the number of transistors, 3. So it will be 3N. So this is if you have transistors in series. What happens if you have transistors in parallel? Because it happens in some logic gates, we have transistors in parallel, transistors in series, right? So it can happen that you get transistors in parallel. So if you have transistors in parallel, let's assume a pull-down network with some transistors in parallel. This is the output, Y, and there is a capacitance here, the straight capacitance, and then we have some transistors in parallel. What happens? Of course, in parallel, if you have transistors in parallel and all of them are going to work at the same time, then the resistance will be 1/3. So here, if you assume that the resistance of this transistor is R, and this is R, and this is R, then when all of them work together, then the total resistance will be R over 3, which means that the equivalent, also the equivalent W over L will be 3 W over L of each of them. So here let's assume it has W over L, or the design has W over L, W over L, W over L. So the equivalent W over L will be 3 W over L. So by the way, if the transistors are in parallel, it appears as if W over L are in series, because W over L is opposite to R, right? R will be in parallel, R parallel with R, parallel with R, so it will give you R over 3. But W over L, because it's inversely proportional to R, it will appear as you are adding them. This is the case that all of them, all branches are on. So if all the branches are on, the resistance will be divided by 3. If one of them only is on, if one branch only is on, then the resistance will be R. But what happens is, sometimes when we use the logic gates, sometimes one branch is on, sometimes 2 branches are on, sometimes 3 branches are on. Which case we should use for design? Which case of them we should use for design? Should we use the case that the 3 branches are on? or the case that the two branches are on, or the case that only one branch is on? As an engineer, think about it. Take a moment and think about it. Which case we should use to design our W over L? Of course, we should consider the worst case, because the worst case is the one that is going to give you the highest delay, the longest delay in discharging the capacitor. So the capacitor is going to discharge. Either it will discharge through the 3 branches, or 2 branches, or 1 branch. What's the worst case? What's the case that will give you the longest delay? The case that will give you the longest delay is the case where the resistance is the highest. And the resistance is the highest when only 1 branch is operating. So the worst case here, this is the one that we should use for design, is when only 1 branch is on. This is the worst case, and this is the one that we should use for design. So when we design parallel branches, you should consider that only one of them is on. Okay, so here now we have parallel branches, and we need to design their W over L. So you will say the worst case is that this branch is on alone. So you should design the resistance of this branch alone to be the same as the resistance of the pull-down network in the inverter. So you should design the resistance here to be Rn, and the resistance of this branch alone to be the same as the CMOS inverter. The resistance of this branch alone to be the same as the CMOS inverter. So that when any one of them works alone, which is the worst case, the capacitor will see the same resistance that it used to see in the CMOS inverter, right? So when, again, in the worst case, when only one of them works alone, is on alone, then the capacitor will see the same resistance, Rn, that it used to see in the CMOS inverter. When many of them works together, then this is better, because the resistance will be smaller. The capacitor will see smaller resistance. So here we should design based on the worst case, and in parallel case, we should design the resistance of each branch to be the same as the CMOS inverter Rn, which means that we should design W over L to be the same as the CMOS inverter. This applies to the pull-down network and the pull-up network. So in the parallel connection, if we have a parallel connection, you should design the resistance of each branch to be the same as the CMOS inverter, and then W over L to be total W over L to be the same here. Okay? While if you have series connection, then the resistance of each of the transistors in the series connection must be equal to the resistance of the CMOS inverter divided by the number of elements in this series connection. So you divide the resistance by the number of transistors, and hence you multiply W over L by the number of transistors. Okay, so this is with respect to the series and parallel connection, and how to design their W over L. Let's see some examples for that. For example, actually, let's keep the examples in the next video to keep the video short. See you in the next video.